of this workshop. We'll have the presentation of Emmanuel about robustness of Markov chain Monte Carlo in parameter estimation of gravitational wave emitted during core bounce phase of the core collapse supernova. Go ahead, Emmanuel.
Thank you very much for the presentation. This is our topic in collaboration with the doctors Michele Sanolin, Claudia Moreno, Javier Mauricio Antelis. Okay, so here's a little bit of the outline of this presentation. I will start with the motivation of this work, then I'm going to introduce the reason why we need an analytical model for doing this task of parameter estimation, specifically of the core bounce phase. And then I will show some of the results of several study cases about the parameter estimation with a LIGO-based Gaussian color noise. Then I will use, for a couple of cases, a real noise from O3 run. Then I will go into details of the prior sensitivity using also this LIGO color noise. And finally, I'm going to talk about, I'll dive into this concept called model comparison using the Bayesian evidence calculated with these parameter estimation techniques. So the motivation, well, according to the sets of two-dimensional axisymmetric simulations from, for example, Richer's catalog and Abelkarov catalog, which is more recent, we can say that the core bounce phase of the gravitational wave producing during this rapidly rotating core collapse supernova can be templatable. This means we can propose an expression or a phenomenological model for the core bounce phase and perform parameter estimation, mainly on the rotational parameter, which I show right in here, which we decided to call beta. Is just the ratio of the kinetic rotational energy against the potential, the binding potential gravitational energy. So, as I mentioned, well, these sets of simulations allows us to understand a little more better this core bounce phase. And of course, since it is present in almost of these simulations for rapidly rotating core collapse supernovae, we propose a phenomenological model. This was proposed in this paper. And the difference is that they used in this work just three free parameters, let's say beta, the rotational rate, tau, the time at which the bounce occurs, and finally also a phenomenological parameter, alpha, which controls the amplitude of the third peak and is hoped to be related to the post-bounce oscillations. And well, in this work, we decided to add one parameter more. In this case, we call it S. And this parameter S controls the Gaussian functions inside this expression. It's just related to the width of the Gaussian belts. So in some sense, it controls the duration of the collapse. As we can see in these plots, each of these parameters affect the gravitational wave amplitude in different ways, right? The beta dependence is just the amplitude of the three peaks, and then the tau parameter is just like a time slide, the time at which the bounce occurs. Alpha and S, well, I already talked about them. And basically, well, this function is a sum of these exponentials, which depend on these HIs, H1, H2, and H3. Which are just the amplitudes that depend on beta, the parameter alpha, just the third peak. Okay, once we have this analytical model, this phenomenological model, the idea is to apply it or to use it for parameter estimation, because we already defined a model, a parameterized model of this waveform. So we start with the Bayesian approach. We use the Bayesian inference, specifically with Markov chain Monte Carlo. So we assume that we have, in this case, a time series called d of t. Of course, we simulate this time series by injecting signal in noise, in the two kinds of noise that I already mentioned. And of course, for this Bayesian approach, we need a Bayes theorem. So in the left-hand side, we just have the posterior probability density function of the parameters depending on this observation. And in the right-hand side, we have the likelihood function, and we assume Gaussianity in this case, defined by the inner product. And the other elements of Bayes' theorem, well, are the prior distributions of the parameters, the information we have a priori of these parameters. And in the denominator, we have this quantity, marginalized evidence, which acts as a normalization constant of Bayes' theorem and is estimated according to this expression. Of course, one of the drawbacks of Markov chain Monte Carlo is that we cannot calculate explicitly this quantity, but we used nested sampling for these purposes. So we use mainly Markov chain Monte Carlo for drawing samples from the posterior probabilities for each of the 4 parameters that I previously defined. And of course, we need a way of knowing if we are estimating these parameters correctly. So for this, I decided to use 3 different quantities. The first one, this is not closely related to the quality of estimation, but it will allow us to compare the relative probability of occurrence between 2 hypotheses or models that explain the signals of numerical simulations. So in this case, if this factor is smaller, very small, this is more than 1, then it means that the model which has the evidence in the denominator is preferred. So it has a higher, it is more able to explain these data or these signals according to the model that we proposed. Then we have this other quantity called the Occam factor, which measures model complexity. This is a quantity obtained from information theory, and basically it compares the standard deviations from the posterior PDF and the prior PDF, and if it is a very, very small value, we face a situation that in machine learning is called overfitting. So we have a lot of parameters or the model that just perfectly fine to data, and it lacks of generalization a little bit. And well, finally, we have the fitting factor, which allows us to test the similarity between 2 different waveforms. After, in this case, we will calculate this quantity for the original signal from Richard's catalog. Then we will calculate the fitting factor with the reconstructed signal with the parameters obtained from MCMC. Okay. So these are the first results of the first study case, and we decided to perform parameter estimation on the signals from Richard's catalog. We didn't take all the almost 100, the 1800 signals. We just use 126 signals summed up in this table, selecting these rotational profiles, angular velocities, equations of the state, and the number of profiles we took from each of these characteristics. And well, after this parameter estimation process, I show in the left panel one random realization out of the 126. And of course, we can see these corner plots from the parameter estimation results. On the top of these, we have the estimated values for each of the 3 parameters. We decided to left S out in this case. And well, this random realization was a LIGO Gaussian color noise based on the PSD at 30 kiloparsecs, and this is the name of the signal. Basically, it stands for the rotational profile, the angular velocity, and the equation of state. Okay, so in the paper that I mentioned previously by one of our collaborators who proposed the model, she uses a very different method for parameter estimation called match filtering, the frequentist match filtering approach. So using her values for the parameters and the values obtained with MCMC, we decided to reconstruct the signal. In this case, this is just one of those realizations, and we can see that MCMC, the green curve is nearer from the is closer from the other curve, the waveform from Richard's catalog, corresponding to these parameters estimated with both methods. But of course, this is just one realization, And for the 126 signals that we chose from the catalog, here in the left panel, we can see the outcome factor, which I mentioned. It is just a measure of model complexity, and it is in the order of 10 to the negative 31, 32. So this means that this value is very, very small, which suggests the situation I already mentioned, which is model overfitting. This is, we are using a lot of parameters for describing the core bounds, or we are not using significant parameters for describing this phase. And on the right panel, we have the fitting factors in the horizontal axis, which correspond to the fitting factors calculated with this frequentist match filtering approach. In the vertical axis, the fitting factors with the reconstructed signals with MCMC, and 68.3 of the signals have a greater fitting factor than the ones reconstructed use match filtering, which suggests that MCMC allows us to get more precise values of these parameters. But of course, we remember that these are just the injections in the LIGO color noise, so the noise might have some implications in these results. And then we decided to use a real O3 noise for this parameter estimation with MCMC. In this case, we found some these results in the left. The vertical orange lines just represent the values for the parameters used calculated using the frequentist approach with match filtering. And then in the right panel, we can see the same reconstructed signals, but in this case, we haven't calculated or estimated parameters for all of the 126 signals because just used 3 different values for beta. In this case, high value for beta, a medium, and a low value. And of course, all of these were estimated using MCMC and the corresponding, the frequentist approach and the corresponding MCMC value with the standard deviations. We observed that those signals that have higher rotation rates show a little bit of, lower rotation rates show overestimation and uncertainties in these values for the parameters estimated. So this might also be related to noise because we have a very small distances in this case. Then the next study case is about the prior sensitivity, also in LIGO color noise. For this case, we decided to run 37 injections of 10 kiloparsecs and individual cases, which are summed up in this table in the lower left corner. So the plots in here is just a reconstruction of these posterior probability density functions for different priors. In this case, we used the log uniform prior, the triangular prior, and an uniform prior. And we can see that almost in the 3 parameters, the parameters estimated were S, the rotational parameter, and parameter alpha. And in this case, we can see that the log uniform and uniform priors show a more tendency of being centered at the real injected value for this signal. And the triangular is a little more broad and has more uncertainty in the process of parameter estimation. Okay. We, of course, in individual cases, we took 2 values also for beta, a low value for beta and a relatively high value, in this case 0.02 and 0.08, and estimated these values for beta using different priors. And we found that in this case, for low values of beta, we have also a lower standard deviation, lower uncertainty of the estimated parameters. And of course, this might be, or this shows some kind of prior sensitivity with respect to the estimated values from the posterior. Okay, in this case, after running these 31 injections, we decided to use now two different uniforms. In this case, we estimated beta parameter in two different cases, also in LIGO-colored Gaussian note. In the left, we can see this estimation at 10 kiloparsecs using both uniforms. In this case, the uniform in beta and uniform in beta squared. And it turns out to be that for our uniform in beta, in both cases, we have a overestimation, but the uniform in beta is closer to the real injected value, in this case 0.06. And well, we have a larger overestimation for the uniform in beta squared. Of course, this is for 10 kiloparsecs, where the noise is a little more notorious in this case. In the right panel, we can see this same realization with the same injected parameter, but at a distance of 1 kiloparsec. In this case, it makes sense that the estimation is almost, the distributions are centered almost in the injected value. But we also see this higher, or this broader posterior probability distribution for the parameter estimated using a uniform in beta squared, which suggests a higher standard deviation, also a higher uncertainty in this parameter. Okay. So for the last of the study cases, we decided to calculate the evidence using nested sampling for 4 different models. In this case, we don't have another model, another analytical model, but if we vary the number of free parameters in the models, we can get different models in a certain sense. For example, if we use a model which considers 1 free parameter, in this case beta, we have 1 corresponding model. Then if we use 2 parameters, we have a model, a different model. And the idea is to test which number of parameters is more useful for describing this core bounce phase. We might not need all the parameters that we proposed initially, and okay, this part tries to answer that question. So here in the left panel, we can see that this is the estimate of the evidence, but we calculate the natural log of the error when estimated or when calculating the evidence. So we see that the models called CBS1 and CBS4, this is 1 and 4 parameters respectively, show a smaller error when are estimated when we are calculating the evidence. And here in this table, we summarize the base factors for the models. In this case, we are comparing them according to the evidences calculated. And we also find out after doing these comparisons that these the more useful models, or the models that better describe the signals from the catalogs, are the model of 1 free parameter. This is just using beta, or the model that shows 4 different parameters, in this case considering beta, tau, alpha, and S as free parameters, and the ones that determine this signal in the analytical model. And well, after this, we decided to use real noise from the O3 run, also at 10 kiloparsecs, but trying to understand this model comparison, but using this match filtering approach. And if we use this match filtering approach for just 1 parameter, this is, if we assume that the model depends on 1 parameter, in this case beta, the fitting factors, or the maximum fitting factors that we calculate, are in the average of 23% and 16%, the median in this case. And if we let the 4 parameters to vary freely to adjust to the waveforms, we get this fitting factor, a higher fitting factor of 87.21% as the average, and a median of 87.8%, which shows that it is more useful to have more parameters in the analytical model that we initially proposed. And of course, these conclusions of the the study cases say that the Bayesian evidence suggests that we should stick to this 4-parameter model because they are more likely to explain the signals from numerical simulations. But of course, we need to also do these same tests for other catalogs, not just for Richard's catalog, to avoid this situation of overfitting. And then this, of course, the advantage of Bayesian inference is that it allows us to refine the analytical model to find a better fit for not only just one catalog of simulations, but several number of catalogs or different waveforms. And of course, we see that it seems to be like this prior sensitivity that introduces some bias and uncertainty if we change the priors in a certain way. So we need to be more certain of how we define these priors and how we can understand better also if this bias is introduced purely by the prior sensitivity, or it has to do something with noise. And of course, using this real O3 noise requires this further data processing because we used whitened techniques to keep this Gaussianity assumption. So the distances, in spite of doing this whitening process, resulted very, very small, 5 kiloparsecs. So we have to see if we can generalize this for larger distances using real O3 noise. And of course, the prospects are this: perform a parameter estimation also in the Avila catalog, use this O3 noise and a network of detectors to improve the way in which we do this parameter estimation process, and include 2 polarizations of this metric perturbation. And at last, to improve this analytical model, introducing a physical significance or a stronger physical significance to these parameters. And that's all. So thank you very much for your attention.
Thank you. We have just time for one quick question. Is there a question for Emmanuel?
How long does your Bilby model take to run?
Well, it's really like 1 or 2 hours for running, but this is just like for 5 injections. For the 126 injections, it took a lot to run, almost a week.
Okay, let's thanks Emmanuel again.